Hello, everybody, and welcome to another wonderful day of chemistry. So today we're finally get a chance to talk about chemical solutions, which is more or less just a liquid mixture of two or more materials. And it turns out that most chemical reactions are actually going to occur in solutions. And one of the reasons why is that when you have multiple species dissolved in a liquid, this is usually when they're most able to see other chemicals, react, move around, and do all of the various things involved with chemical reactions. And it is worth noting there is a big range of chemical solutions out there because you can be dissolved in any number of materials. But one of the biggest ones that you're going to encounter most commonly, and so we're going to talk about the most, are going to be aqueous solutions. So essentially where we have things dissolved in water. Now, in order to talk about solutions, we need to bring up some terminology because a solution involves two parts: the solvent, which is the liquid phase, and it's the dominant component of the solution. So whatever the dominant or most abundant material in the solution is, that's our solvent. Our solute is going to be the minor component. So usually it's a solid that's dissolved in a liquid, but again, not always. When these two things mix together to form a homogeneous solution, well, that's our solution. It should be homogeneous and an even mixture. As soon as it becomes heterogeneous, all of the same rules all of the rules we're going to invoke kind of go out the window. And most of the time when we're looking at chemical reactions, the solvent is usually relatively a spectator. It just facilitates things moving around. The reaction occurring usually involves our solute. But here's going to be the problem, because we've already known that in order to determine how a chemical reaction occurs, we need to know how many moles of solute we have. And that works fine if we measure out our mass of the solute, but most of the time, all we have is a mass or a volume of the solution. So I need some way to tell exactly how much solute is present in a given volume of solution. And because what we really care about is the reactive component, we need to be looking at the moles of that solute. And because it's the easiest thing to measure out, we're going to be looking at moles of the solute in liters of solution. And this has a special name and unit. It's called molarity. So if you see a big M, I'm referring to the molarity of a solution, which is just a fancy way of saying moles of whatever solute over liters of the total solution. And this is actually a really easy way to help quantify the number of moles of that reactive species using a much more practical and measurable quantity. So if I'm going to be trying to prepare a solution of known molarity, I need to do this by, first of all, measuring out a known mass of whatever I care about. Then I'm going to dissolve it in a little bit of whatever the solvent I care about is, until it's now a homogeneous solution. And then we dilute to the mark. And this is because there is a very important caveat when we're looking at molarity. It isn't moles of solute per liters of solvent. In this case, it would be ethanol. It's per liters of solution. So I need to know that when my solute and solvent are mixed together, that gives me a total volume. And to do this, we use something called volumetric glassware, which is a fancy way of saying it's a piece of glassware with a mark on it that tells you exactly what the volume of a whole mixture is. That way, we can be utterly sure that we have the right volume for the total solution. And this kind of makes sense that if I'm adding my solute to my solvent, it can change the volume. If I go ahead and throw salt and water, I would expect the volume of my solution to go up because I put more stuff in it. And that's exactly what we see here. But once we have, and we can go ahead and predict exactly what the molarity of a solution is if I know the mass of the solute I added and the volume of that resulting solution. One of the nice parts is a lot of these volumes tend to be very even numbers because that's what those volumetric glasswares come in. For in this case, a 200 milliliter solution made by dissolving about 3.4 grams of ammonia. By the way, in case you're wondering, this is more or less how you make Windex. It's ammonia dissolved in water. So let's go ahead and figure out what the molarity of this reasonable cleaning solution would be. So in this case, I'm looking for units of molarity, which is a ratio of amount to volume. So I'm going to start by doing a ratio of amount to volume, in this case, grams to milliliters. But since molarity should have liters in the bottom, I can go ahead and convert my milliliters to liters. And since it should have moles in the top, I can convert my grams to moles. Go ahead and double check. Our units should cancel out. And we should have moles of ammonium hydroxide, moles of ammonia per liter of solution. Now we can go ahead and plug in our conversion numbers, including the molecular weight of ammonia and 1,000 milliliters in a liter. When we do this, it turns out that this is going to be a 1 molar solution. This kind of gives you an idea of what sort of concentrations are involved in 1 molar of a substance. So in ammonia's case, this would be about 3.4 grams per 200 milliliters, or closer to 15 grams per liter. Now, it is worth noting that the amount of substance that goes in will be very different as you change the molecular weights. Because again, when we're dealing with molar concentrations, we care about the amount of molecules, not their mass. And that's an important thing to keep in mind as we go forward. However, most of the time, if you make a stock solution, you won't use it at that concentration. Most of the time, we're going to be adding extra solvent to help dilute the system. So next time, we're going to be talking about that most practical of topics, dilutions. Until then, take care.